Hey, what's up, guys? So today I want to keep introducing some inequality. Basically, is the concentration inequality. Okay, so like Markovian inequality or the Chebyshev inequality, they are both called the concentration inequality. And today I want to introduce another famous called the Hoeffding's lemma inequality. So basically, there are in the probability distribution, there are some inequality that you can relate it to your expectation value and the variance. And okay, so this kind of inequality is called the concentration inequality, and there are various of them. I think the famous one is the most famous one is the Markovian inequality. So basically, you can ask the probability of you if let's say you have some finite probability distribution, and your x minus mu, which is your mean, if you greater than something, then you should able to bound this, right? So you should able to bound this guy by something, right? And I remember it correctly, it should be, let's say this is a, and it should be e of x divided by a. If all x are positive, and then the second is that the Chebyshev inequality. Chebyshev inequality that you can ask how many let's say your results greater or equal to, let's say you larger than let's say the variance with a k times, then you should prove that it at most one of k squared times something. Okay, so this is the Chebyshev inequality and the Markovian. So basically, all these inequalities that why it's called concentration, because that if you think that that's a central limit theorem or something, that you get some probability, and so you get some understanding of your first moment or a second moment, basically it's a variance, then you should able to then so basically you have some mean and the variance, right? So anything if you deviate the mean or the variance a lot, then you should have expect that there should be some bound number which is bounded above. Okay. Okay, and this Hoeffding's lemma is basically also doing for this kind of function, but with the explanation. Okay, so let's introduce Hoeffding's lemma. So I will prove this, and once I prove this, then I will prove another basically inequality version, and I will talk about one example. Okay, so the start point is that let's say you have x, which is a random variable with real values, and then let's say you imagine that there's a it's mean, and you know that x belongs to a and b almost surely. Okay, so if you don't care about almost surely, you can say the basically this means that all the x between a and b must be 0. So basically, this just say if you like the major theory language, you can say that the x which is larger than b and less than a has 0 major. Okay, and now for all lambda belongs to R. So remember the Markovian and the Chebyshev, one bounds the mean, one bounds the variance. For this one, you can bound the exponential, right? So basically, you can prove that exponential on x. I should say minus the expectation value x, which is equal to less or equal to square b minus a squared divided by 8. Okay, so this is a little bit interesting. Okay, so it says that you can bound these terms is less or equal to something, which is a little bit weird compared to this. Right, because you imagine that if your x is only 1 point, right? So this expectation value should be very central, right? But now, but at least you can bound something which is above, which bound this exponential difference. Okay, so proof. The proof is basically the simple idea is that you first just shift your probability distribution, so you can assume that ex is 0. Okay, so now let's write down everything you have. So the notice that exponential lambda s is convex. Okay, so convex means that the f of t1 plus, sorry, not t1, tx1 plus 1 minus tx2 is less or equal to tf of x1 plus 1 or minus tf of x2. Okay. And the exponential lambda is convex on all the real numbers. Okay, the reason is that you can do the differentiation, and yeah, that's it. Okay. Okay, yeah. Differentiation twice, right? You get some positive function, right? Because lambda square is always positive. Okay, so now you can easily check that if initial lambda ta plus 1 minus db is less or equal to this, right? So you just consider f of x to be exponential lambda x. You get t of exponential lambda a plus 1 minus t exponential lambda b. Okay, okay. Okay, so combine all of these, right? You can take this and then combine, you get exponential lambda. Let's say choose. Let me just choose. So I can choose t to be b minus x divided by b minus a. Okay, so you combine this, right? You can do some simple computation. You get ba minus ax divided by b minus a plus b minus a, bx minus ab. Right? This is less or equal to b minus x, b minus a, exponential lambda a, and then you take 1 minus t, right? So 1 minus t will be minus a, b minus a. I usually get the minus a, b minus a, exponential lambda b. Okay, and you can easily check this. This is just exactly x. Okay, so you get exponential lambda x. That's equal to b minus x, b minus a, exponential lambda a, plus x minus a, b minus a, exponential lambda b. Okay, so now you can bound this, right? So now once you have every kind of formula, then you can take the exponential left and right hand side. Okay, so we take exponential. Sorry, not take exponential, take expectation value. Okay, so you get an exponential lambda x, expectation, not exponential, expectation. That's equal to b minus expectation ex, b minus a, plus lambda a, plus expectation x minus b, b minus a is lambda b. And then from my perspective, I already first assume that ex is 0. Right, so this is b minus a exponential lambda a plus exponential lambda b minus a, b minus a. Okay, so now when I can find what I can try to bound this guy, right? So so the idea is that you just use your calculus, right? You use calculus. This is same as in like the Chernoff bounds, right? If you want to prove some probability distribution and the right hand side is some function, then you usually guys that you need to find a minimum of this function, right? Because now you will get a tighter bound. You will get tightest bound if you find the minimum of such function. Okay, so then everything should be trivial. So let me just quickly say what's going on. So you can write this guy as an exponential LH. Sorry, let me just write the exponential LH. What is LH? So LH is minus HP plus log 1 minus P plus P exponential H, and H is lambda B minus A, and the P is minus A B minus A. Okay, so you get this, right? Okay, so this is a simple calculation. Okay, so let's write down LH is minus HP plus log 1 minus P plus PEH. Okay, so simple exercise. If you put H equals 0, you get 0. Okay, because this is 0, this is 0. Okay, and this is 1 minus P plus P. And then if you first do a derivative on H, you get minus P plus 1 minus P plus P of H. Okay, and you do another differentiation, right? So you get P to H, and then you put H equals to 0, you get minus P plus P, 1 minus P plus P, still 0. Okay, so now you can use a Tyler's theorem. Okay, if you haven't seen the Tyler's theorem proof, that you can I will post my advanced analysis. Basically you just follow the routines proof. So basically you can prove that so if you do the LH minus L0 minus H of L0 prime, this guy is less or equal to what? The differentiation, the second derivative, right? So half L prime of x and H squared, such that you take absolute value and X choose to be, let's say, 0H, right? So this is the Tyler arrow, okay? And right, so you just do a second derivative, and you can prove this less or equal to, I think it's 1/8, okay? Okay, times H times S squared, okay? Right, H squared is always fixed, right? So the second derivative you can prove is less or equal to 1/3. Okay, so basically you can prove this. Okay, hopefully it's not so difficult. Okay, so finally, your expectation exponential lambda x, expectation of exponential lambda x is less or equal to this bound, right? So you get a exponential 1/8 b minus a squared lambda squared. Okay, remember that my definition h is lambda times b minus a. So this is 1/8 b minus a squared lambda a squared. Woo. Okay, so this is the lemma proof. Okay, it's not difficult. Okay, so yeah, this is the lemma's proof. I think you can check the detail. I mean, this is all detail. Okay, so we have the theorem, which is Hoeffding's inequality. So this one is like people somehow use, right? So basically you have some x1, x2, which is independent variable. So usually you have independent variable, right? Draw from something, and you will try to do the sampling, right? So so in this case, let's imagine that I know some bound for the. I think this is also practical, right? You know some bound for your variable. Okay, then and then you can take your x bar to be, let's say, 1/n, to be another random variable, which is x1 plus xn, and also usually people use sn to be x1 up to xn, right? And so basically, you know, ex bar is basically 1/n, the summation of xi bar, right? So just just the expectation value of xi. Okay, so it's very natural to ask how to bound this guy, right? How to bound this, how to get some lower bound, right? The higher low the sorry, how to bound this guy, right? So you want to ask whether x bar minus ex bar is greater or equal to t. So this guy looks like Markovian, right? So the you can use a Markov inequality, right? So that's what we're gonna to use, is less or equal to exponential minus 2n squared t squared, and the summation of bi minus ai, I from 1 to n squared. Okay, so this is the bound. Basically, this is also, so this is why I call the concentration inequality, because if you're greater or equal to the expectation value, then the something will bound you. Okay. Okay, so this is the proof. This is the theorem, and let's go to the proof. Okay, I think the statement is clear. Okay, proof. Okay, and this by the way, this guy is the same as p of xn minus its potential xn, right? Greater or equal to t. You just need to modify a little bit, right? You can change it into this. This is exactly the same, if only if by just changing just times n and change do the change of variable. Okay, so proof, consider Sn to be x1 up to xn, right? And then you take and then you want to ask this, right? So minus this. Okay, so now you use you just make this probability of exponential Sn minus exponential Sn greater exponential St. Okay, so S is just some real numbers. Okay, so now one can use Hoeffding's lemma. Okay, so from this is so now you see why we use this kind of theorem. Why we use why Hoeffding's lemma use this exponential version, because you can, so usually sometimes doing the probability distribution on the sum of the random variable is difficult, so you can use this to make it into exponential, right? So Hoeffding's lemma. Okay, so I now I use Hoeffding's lemma. Right? I can pull out this exponential minus St. It becomes less or equal to exponential s. Oh, by the way, and not so fast. This is so fast. So first, this is the Markov inequality. Okay, so once I use Markov inequality, then I can change the probability into expectation value, right? And the expectation value is bounded by Hoeffding's lemma. Okay, so this is this. And the thing is independent, right? So I can make it into product. Okay, nice shot. Now I can use the product. Okay, so by Hoeffding's lemma, so this guy is less or equal to exponential minus st summation I from 1 to n and exponential s squared bi minus ai squared divided by 8. Okay, so you just I from 1 to n. I should say exponential minus st plus summation I from 1 to n s squared bi minus ai squared divided by 8. Okay, so this is quadratic in s, right? And the coordinate, the square term is positive, right? So you can find a minimum. Okay, so find a minimum. Yes. Okay, once you do this, then you get the bound, right? You get a minimum bound, right? So you get a bound. So this guy is greater or equal to exponential minus 2t squared summation bi minus ai squared I from 1 to n. Okay, so this is your bound. Okay, so this is your bound. Okay, so now we prove a Hoeffding's inequality. Okay, so let's see. Yeah, this is the usual step that people can do. Okay. Yes. Yeah, let me just talk about one example. This example is, I think, is also common. Okay, so example, just the application. Okay, so consider you have a coin, which you got P to be, you got probability P to be positive, and then 1 should be negative. 1 minus P. And you can let H of n, right, to be, let's say you throw in coins again, you throw in coins, and the number, and they are independent, so this is a number of heads. And so I can ask, what is the bound that you can bound? What is the probability that the number of heads less or equal to k? And basically, you can compute this, right? This is high square problem, right? Just n choose k, p to the I, 1 minus p I minus I, right? You can prove this by using this is just from high school, right? But I want to get the bound, right? So I want to get some bound that which is easy to dealing with compared to this binomial coefficient. Okay, so I just take, let's say I take k to be, so what is the expectation value, right? Expectation value to get heads is basically np, right? Because you take n, so e of hn, right? By the way, e of hn is also a random variable, right? So we get np. Okay, so what is the k? Okay, so I want to use the bound. I can ask, what is the p of hn minus np, right? And the greater or equal to something. Maybe let's say basically I want to bound this guy, right? I want to bound this guy. Okay, or basically basically another directions. Okay. Okay. Okay, so let's do this. So from your previous inequality that I noticed, right? So let's say I greater than np plus epsilon, and this is just p of hn minus np greater or equal to epsilon. This is less than exponential minus 2n epsilon squared. Okay, this is by our Hoeffding's inequality. Okay, so by Hoeffding's. And the reason is that this is exponential 2n squared minus epsilon, right? And then you get sum of that, right? So you get that. Okay, so basically, let me just write down. Remember that what we already proved is that PSN minus exponential SN greater or equal to T is less or equal to exponential minus 2T squared summation BI minus AI squared I from 1 to n. Right? So in this case, that everything is this BI and AI, and by your definition, should be half or minus half, right? So it should be 1. And the n of length, right? And then you change it into n epsilon, right? So this is t, you need to go to the n epsilon, and your bi minus ai is 1. And then you get this. Okay, and then you can easily check another. You can easily prove the same thing, right? You can easily prove that h of n less or equal to p minus epsilon n is also less or equal to exponential minus 2n epsilon, right? Because these are what? These are symmetric. Okay, so combine everything, you get p of p minus epsilon n less or equal to h of n. P plus epsilon n, right? Is greater or equal to 1 minus 2 minus 2 and epsilon squared. Okay, right? Because I use minus this. So P of h of n minus P of n, let's say, right, so this is our result. So basically this is also concentration, right? Because I proved that the concentration between the average with the epsilon should greater or equal to something, right? So this bound is non-trivial. Okay, so for example, let's say choose epsilon to be log n divided by n, then you can prove the following, right? This is n log n will greater or equal to 1 minus exponential 2n log n divided by n. This is 1 minus exponential 2 to the log n. It's 1 minus 1 over n squared. Okay, so this is very non-trivial, right? It's very non-trivial to see this is true. So let's say that, for example, exponential 10, is 10, then you can prove that if you choose the number of heads, right? The number of heads minus, let's say, p is half, the number of heads that you get, probability h10 minus 5, less or equal to something. These kind of probabilities is greater or equal to 1 minus 1 over 10 squared. Right, so basically you can prove that this guy is greater or equal to something. So now from this you already proved that the like central limit theorem, right? If you take n to be large, or all of the arrow to be large, but basically these type of things, yeah, you can control. Okay, so this is our very non-trivial results. Okay, so see you guys next videos.